Hi and welcome to my video introduction to integration. Another name for integration, of course, is anti-differentiation. You'll probably see both, but we'll trend more towards integration later on. So in this video I'm going to introduce it, and because I'm introducing it, I'll probably deal with just the polynomial side of things and talk to you on a really basic level to do with that. And then hopefully you can move forward into the other functions as we move forward with the topic. So this is a Unit 3 Math Methods topic, and here we go. So you've done some polynomial differentiation. Let's say we started with the polynomial y equals 3x cubed. Okay, now I could derive this fairly easy. I get my dy dx function. I bring my power down the front as a multiplier, so I get 3 times 3x, and I subtract 1 from the power, giving me 3 times 3x squared. And of course, that's now equal to 9x squared. So this is my rate of change or gradient function for the function y. Now, in these situations, what if you're given dy dx, but you want to know y? That's what anti-differentiation is. So I'm just going to rub that out. We'll pretend like we don't know it. So, welcome back, and I've just rubbed that out. We've got a differential. We don't know what the original function was. And this is where anti-differentiation comes in, which will eventually lead to integration. And integration itself has a really great amount of good contextual purposes. So let's start with this though. 9x squared is dy dx, and I want to know what y is equal to. And if you watch the first minute of this video, you already know what y is equal to. But let's just take a second and think it through. When I derive a function, this is a polynomial, so I know it's going to be in this form, ax to the power of n. It's going to look something like that. When I derive this, to get to that, I would have decreased the power by 1. So that n is decreased by 1 to get 2. Okay, so I already know that this is going to be something x to the power of 3. The only way to get to an x squared function, if I derive, is to have an x cubed function to start with and derive it to x squared. So that's the first part. Now I've got a and n to deal with here. I already know my n. But if I derive ax to the power of n, or in this case something x to the power of 3, when I derive that, I'll get a factor of 3 at the front. And that contributes to my 9. So when I integrate or anti-differentiate, I need to do the opposite. I need to reduce it by a factor of 3. So what I'm going to do is I'm going to divide it by a factor of 3 instead of multiplying by a factor of 3. And it's not just 3 every time, of course. It's the power, and more specifically, the new power. And of course, I've got a 9 factor there, so I'll leave my 9 factor there. And now if I just quickly rub this out, here we are. Then my 9 divided by 3 is 3, and I've got 3x cubed. I've done that fairly long-winded though, so I'll talk more generally about this in a second. The fact here is though, if I start with my function, I know that when I anti-derive, the power has to increase by 1, but when I derive the original function, I will have multiplied by my new power, so I have to divide by new power, and the 9 just stays there as an incidental coefficient. So the rule is that if you want to anti-derive a polynomial, then, and you start with dy dx is equal to ax to the power of n, well, my y function will be equal to, the a stays, x to the power of n plus 1, I have to increase the power by 1, but now I have to divide by the new power, which is n plus 1. That will take me back to my original y function. There's a couple other things I have to worry about though, and I'll give you a bit of introduction to polynomials. What I'm going to do is run through some examples of polynomials in the next video. For the rest of this video, I'm going to talk to you about the specific notations and some of the ideas that we need to consider, and I'll do it through a single polynomial example. So I'm just going to rub this off and then we'll start that. Okay, so we're talking about getting our function, which is dy dx, as a gradient function, and we're saying ax to the power of n is our generalized polynomial, and we want to get the original function, y equals ax to the power of n plus 1, and of course we divide by n plus 1 to get there. So that's our reverse. There's a couple of things. First of all, I'll start with this example. Dy dx equals 7x cubed. So we'll run through this example. Now, the first thing is the notation. So if I want to anti-derive, another name for that, as I mentioned earlier, is integration. And there's an integration sign. So y will be equal to the integral of 7x cubed with respect to x. That's how it's stated, but let me take you through it. Y, we're heading towards our original function, equals this thing here, which actually looks a little bit like I've elongated an f, but it's kind of like a stretched out s, so I probably shouldn't have rolled it over. It looks a bit more like that. So that's an integration sign. It's probably going to be taller than your function. 7x cubed, that's your function, that's your dy dx, with respect to x. So we're integrating with respect to x. This probably won't seem important as you go through the next year of your studies, but if you move into some more complex mathematics, sometimes you might have a function which has two variables, and you have to actually define, are you integrating with respect to x, or with respect to y, or with respect to w, etc. But for now, this is just a notational thing. And so when we solve this, we get 7x to the power of 4, I raise the power by 1, and I divide by the new power. I could write that down as 7 over 4 x to the power of 4. That's pretty much all I want to cover for this video, except for one thing. This is definite integration, and we'll explain that a little bit more later on, but there's one other little thing we have to concern ourselves with, and that's this. Let's imagine we did the reverse on that. Let's imagine we have y equals 7 over 4 x to the power of 4, and we wanted dy dx. Dy dx would obviously be 4 times 7 over 4 x to the power of 3. Bring the power at the front, decrease the power by 1, and that of course is equal to 7x cubed, which is what we started with. So that's good. So we've got that, we're happy with that. What if I started with this function though? Y equals 7 over 4 x to the power of 4 plus 5. Or plus 7, or plus 100, or minus 10, or plus pi. Whatever that number is, it's just a number. If I derive this, hopefully you'll see that the 7 over 4 x to the power of 4 will become 7x cubed again. The plus 5 will just disappear. I've actually got the same answer. There's actually a whole bunch, if I integrate this or interdifferentiate this, I'll get a whole bunch of things here. So what we have to do is recognise that, and this is now a more general, when you integrate a function, ax to the power of n, with respect to x, it's equal to ax to the power of n plus 1 over n plus 1, but there might be some constant added to the end. That little number there might exist. Might be 0, in fact it always exists, it might just be 0. But it might be 7, it might be 5, it might be pi, it might be negative 100. We don't know. And until we have more information we can't really tell. So we always have to have a plus c, which is called the constant of integration, and we just include it on the end of our integration. And we'll start to learn how to deal with that later. Anyway, that's a basic intro to integration. I'm going to run through some videos now where I show you how to do each of the different types of integration. All the best.